Yeah, in this video, I'm going to discuss about the substitution nucleophilic unimolecular reaction. Yes, uh, yes, the substitution nucleophilic unimolecular reaction, which is represented by SN1. Yes, S with substitution, N for nucleophilic, and 1 is unimolecular. Yeah, let's see in detail now what is the substitution reaction first and then go for SN1 reaction. Yes, so let's understand what is first substitution reaction. Okay, substitution reaction simple. As the name suggests, a substitution is nothing but if you take a reaction, suppose if an atom or a group has been substituted by another atom or a group, then it is called a substitution reaction, right? So the name itself is suggesting if it is substitution nucleophilic. Yes, let's understand this term nucleophilic now. Yes, when we go for an example, this alkyl halide, the C connected to the X is nothing but an alkyl halide. When it is attacked by a nucleophile, yes, what is a nucleophile? A nucleophile is nothing but an electron-rich species. Yes, it is an electron-rich species, which means that it is go for an electron deficient species. So when we come to the nature of the CX bond, we have learned that this one because the CX bond is highly polar. Why? Because X, if you take an halogen, any halogen, F, Cl, Br, or I, is electronegative. So this we know that the halogen is more electronegative when compared to that of this carbon. As a result, it will try to draw the electrons from the carbon towards it. So it has a tendency to attract the electrons more towards it. As a result, this is polar, and as a result, this will get the partial positive charge and this will get the partial negative charge. This nucleophile has a tendency to go towards the positively charged species. So the nucleophile is directly attacking the substrate where there is a positive charge. This means electron deficient center. So this one is a substrate where the reaction, the nucleophile is attacking, and this is the attacking reagent, right? And this is a product which is being formed. Right after the attack of the nucleophile on this carbon, as a result, X is being replaced by Nu here. So which is replaced? X is being replaced by the nucleophile. As a result, the nucleophile is taking the place of X. X is being substituted by nucleophile. So this is the substitution nucleophilic, where one nucleophile has been substituted or replaced by another nucleophile. So it is a substitution nucleophilic reaction. So this is the meaning, the term substitution nucleophilic. So nucleophilic substitution reaction, and this is the leaving group here. So X minus is leaving from the substrate. So this is the leaving group here. Yes, right. So let's understand in particular the SN1 reaction in detail now. So let's talk about substitution nucleophilic unimolecular. So I'll write here substitution nucleophilic unimolecular reaction. So why unimolecular? Because when we take, for example, the tertiary butyl bromide with the IUPAC name is 2-bromo-2-methyl propane. So this is what? CH3 tertiary butyl group, where this carbon is attached to 3 other carbon atoms, and tertiary butyl bromide, this is a substrate we are using here, as being attacked by a nucleophile, which is nothing but the OH minus, resulting in the formation of tertiary butyl alcohol. Yes, OH, this is CH3, 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 OH, and this is the leaving group. That is the Br minus is nothing but the leaving group. So Lg, represented by Lg here, and this is a product which is being formed. Here the Br minus has been replaced by OH minus. So as a result, we are getting the tertiary butyl alcohol, right? So Br is being replaced by OH. So this is a substitution reaction. As one nucleophile is being replaced by another, that means Br minus replaced by OH. This is substitution nucleophilic reaction. Let's understand now why it is unimolecular. Yes, why it is unimolecular means the rate of the reaction here, I'm saying the rate of the reaction here is proportional to the concentration of the substrate. Yes, and not on the attacking nucleophile. It is dependent only on the concentration of the substrate here, that is tertiary butyl bromide in this case. So the rate of the reaction is dependent only on the concentration of the substrate. That in this case, it is tertiary butyl bromide and not on the concentration of the attacking nucleophile. So it is called as first order reaction or unimolecular reaction. The one is for first order reaction. So this is first order reaction or unimolecular reaction. I said here this is a unimolecular reaction. So follows the first order kinetics because the rate of the reaction depends only on the concentration of the substrate. I'm repeating it, only on the concentration of the substrate. So it is called as substitution nucleophilic unimolecular reaction. Yes, let's understand this, the mechanism of this reaction in detail. Yes, when we go for the mechanism, the reaction takes place in two steps. Reaction takes place in two steps, where the first step where the tertiary butyl bromide has been resulting in the formation of this carbocation intermediate here. Yes, this carbocation intermediate is being formed and the Br minus is leaving here. So the reaction is proceeding through the carbocation intermediate. This is the first step of the reaction. And in the second step, this OH minus is attacking this carbocation intermediate, resulting in the formation of the result product, which is nothing but the tertiary butyl alcohol. Yes. So the reaction is favored in the presence of weak nucleophile. Yes. So the weak nucleophile is just enough for the reaction to proceed here. The stronger nucleophiles, on the other hand, favors SN2 reaction. But for SN1 mechanism, what is required? Only a weak nucleophile is enough for this reaction to proceed. And this takes place in the presence of polar protic solvents. Yes, this is important. Polar protic solvents. Yes. So the use of the solvent is to dissolve the reactants in it. Right. Since we are using the polar reactants here, the polar solvents are to be used and they need to be protic. Why protic? Let's understand it. So the examples of polar protic solvents are water or methyl alcohol and so on. When we take this water here, it is polar because this end gets a partial negative and this is a partial positive charge, right? So this presence of lone pair of electrons on this makes it partial negative and is more electronegative when compared to that of this hydrogen here. Protic solvent because it is able to give the H plus here. So this is the meaning of polar protic solvents. In the case of CH3OH also the same thing. So this is favored by a weak nucleophile and the polar protic solvents like water or methyl alcohol. Yes. Why these polar protic solvents are used in or why these polar protic solvents will favor SN1 reaction? Let's understand this. Yes, I said the reaction is proceeding through the carbocation intermediate, right? So this carbocation intermediate which is formed is stabilized by this polar protic solvents. How? See, this is a positive charge on this, which is formed on the carbon atom. Now, this because of this polarity and its protic in nature, this has been stabilized here by the negative end of this, like this. Yes, on all else. Yes, this is negative, right? So this has been stabilized. And also the halide ion which is formed is been stabilized by the positive end of this water molecule, for example. So, because these are stabilized, the carbocation intermediate which is formed by these polar protic solvents, the reaction is favored in the presence of polar protic solvents. But for SN2, we have learned that the reaction is favored by polar aprotic solvents, because the reaction there proceeds through the transition state. But the carbocation intermediate is being formed here in SN1 mechanism, which is favored by this polar protic solvents. So we use the polar protic solvents here in the SN1 reaction to favor the SN1 reaction. Yes. Now we have learned that a weak nucleophile is enough for this, because here in the rate determining step, see, the step 1 is nothing but the rate determining step of the reaction, RDS, because this is a slow step. So we know that the rate of the reaction is dependent on the slow step of the reaction, and so the step 1 is the rate determining step of the reaction, and the rate of the reaction is totally dependent on the concentration of this substrate and not on the nucleophile. That is why a weak nucleophile is also enough for the reaction to take place. Yes, and yes, let's understand what type of substrates can be used. So we have learned about the nucleophile, the solvent, and the substrate. So let's take this tertiary. This is tertiary, right? So tertiary butyl bromide. This is secondary. This is primary, and take methyl bromide. So I said the reaction is proceeding through the carbocation intermediate, right? So in which case the carbocation intermediate is more stable? Yes, if I take the substrate to be tertiary alkyl halide, then the intermediate, the carbocation which is formed is stable. If I take the substrate to be tertiary butyl or alkyl bromide, whatever, because this carbocation here, the positive charge of this carbocation has been stabilized by 3 alkyl groups here, the plus I effect of 3 alkyl groups here. But in the case of this secondary here, it is stabilized by only 2 groups here. When coming to the primary, it's only 1. So depending on the stability of the carbocation, we say that, depending upon the stability of the carbocation, we say that the tertiary alkyl halides will undergo this SN1 reaction more when compared to that of this secondary, when compared to that of this primary and normal methyl bromide or halide, whatever. So the rate of the SN2 reaction when we go from tertiary to secondary to primary to CH3X, it decreases. It increases. And for SN1 reaction, it increases from methyl halide to primary to secondary to tertiary. Because here I said the carbocation intermediate is being formed, but here the transition state is being formed. Yes. So the carbocation intermediate which is formed, the tertiary is more stable than secondary when compared to that of this primary. So the tertiary alkyl halides will undergo the ascendant reactions faster when compared to that of the secondary when compared to that of this primary alkyl halides. So yes, when we take this again, allyl or benzyl alkyl halides. For example, what is the allyl group? Yes. So what is allyl? Can you tell me? Yes. What is allyl? This is an allyl bromide, right? So if I take this halide, yeah, let's take X here. Yeah, I'll take X here maybe. Yes. If the carbocation intermediate is being formed, for example, it is proceeding through SN1 reaction, then the intermediate which is formed here is, yeah, let's erase this one. Yes. Yeah. CH, yeah, this is the intermediate which is formed. This is nothing but allyl carbocation, right? So the allyl carbocation which is formed here is stabilized by means of resonance here. Yes. Yes. By means of resonance. And when we come to the benzyl, this is a benzyl aldehyde. When this is losing X minus, resulting in the formation of the carbocation. Yes, this is a carbocation which is formed, and this is also stabilized by resonance. So we have already learned this. So let me write the resonance structures for this. Uh, yes, CH2 plus, right? So when I take the resonance structures of this is somewhat the resonance structures of this benzyl carbocation. Yeah, positive charge here. This is what? Benzyl carbocation. So the benzyl carbocation which is formed is stabilized by resonance even in this case. So let me write the resonance structures of this. Right. There's a positive charge here. This is CH2 again. Yeah. So many resonance structures are possible for this benzyl carbocation. As a result, we can say that, yeah, here it is. Yeah. The positive charge here and one more. Yes. So in this allyl carbocation, two resonance structures are possible, and for benzyl carbocation is stabilized by means of so many resonance structures. So we can say that the allyl and benzyl carbocations are more stable when compared to that of this tertiary alkyl carbocation, which is more stable than secondary. Then comes primary, and then comes this methyl cation. So but depending upon the stability of the carbocation, the SN1 reaction also decreases in the following order. So this is the rate of the reaction for the SN1 reaction. Yes. So when we take the optically active alkyl halide, yes, let's turn the stereochemistry of this. So optically active alkyl halide I'm taking here, for example, this case, what is optically active alkyl halide? Let's understand what is optical activity. Yes, so the carbon here is attached to four other groups in this case, CH3, H, CH2, CH3 and Br. This carbon here is attached to four other groups here. So such a carbon is called as asymmetric carbon or chiral carbon. That means it is able to rotate the plane polarized light either towards left or towards right. So the optically active alkyl halide, or the optical activity, is nothing but it can rotate the plane polarized light. If it rotates the plane polarized light towards right, it is called as plane polarized light towards right. It is called as what? Dextrorotatory.
or D form or plus. Yeah. If it rotates the plane polarized light towards the left, then it is called as levorotatory or L form or minus. It's represented by minus. So I said this is proceeding, the SN1 reaction is proceeding through carbocation intermediate now. So if this is optically active, that means if it is able to rotate the plane polarized light either towards the left or towards the right, then the carbocation intermediate which is formed here, this is a carbocation intermediate, right? So in the second step, when it is attacked by the nucleophile, it can attack this nucleophile, I mean this carbocation from the front or from the back side. Yes, it can attack this carbocation either from the left or from the right, from the back side or from the front side. So this is sp3 hybridized, and when we come to the carbocation, it is sp2 hybridized. That means it's planar. This planar carbocation can be attacked by this nucleophile here from the back side or from the front side. So if it attacks the carbocation from the front side, then we will get the product which has the same configuration as that of the reactant here. So this is called as what? So if it is attacking from the front side, then it is called as the retention in the configuration. That means a configuration is retained. So retention in configuration, that is having the same configuration as that of the reactant. If it is rotating the plane polarized towards the left, this is also rotating towards the left. See, this is minus. Now, if it is attacking from the back side, that means the OH minus is attacking from the side opposite to that of the Br, then we'll get the configuration which is reversed. That is, configuration is reversed. That means inversion in configuration. Right. Inversion in configuration. Yes, that means it will rotate the plane polarized light towards the side opposite to that of the reactant here. Right. So as a result, we'll get a mixture which is having 50% of retention in configuration and 50% of the inversion in configuration. That means 50% plus 50%. So this is called as the racemic mixture. So we have understood the new term here, which is called as the racemic mixture, which is having the product which is half of it is retention in the configuration and half of the product which is having the inversion in configuration. And such a mixture is called as a racemic mixture, and the process is called as racemization. Yes. So this is what is SN1 reaction. So if this is happening, that means the racemization is happening or the racemic mixture is obtaining when only we are taking the optically active alkyl halide. Right. If the reactant is not optically active, there is no question of this racemization or whatever. Okay, so let's understand, let's again revise the characteristics of this SN1 reaction. Yes, this is SN1. So this is SN1. Right. So first one is the rate of the reaction is dependent only on the concentration of what? The substrate. That means the alkyl halide, not on the attacking nucleophile. And the second one is it is proceeding through two steps, not in one step. And the third one is here the carbocation intermediate is being formed here. What is formed? Carbocation intermediate is being formed which can be isolated. Which can be isolated, but because it can exist for a brief period of time here. And because the carbocation is being formed, the attack can take place either from the front side or from the back side, resulting in the formation of racemic mixture. If we are taking optically active alkyl halides. In the case of optically active alkyl halides. Right. So, and it is favored by weak nucleophile. That means weak nucleophile is also enough for the reaction to proceed because the rate of the reaction is dependent only on the concentration of the substrate and not on the nucleophile, I said. And also, what type of solvents? Polar protic solvents will favor this reaction. I told you the reason also. The reason being the carbocation which is intermediate which is being formed is stabilized by means of these polar protic solvents like water, alcohol. Right? So these are the characteristics of this SN1 reaction, and yes,